Imagine standing beneath a perfectly dark sky. Thousands of stars glow above you, but what you are really seeing is only a tiny neighborhood inside something unimaginably larger. A city of stars stretching more than 100,000 light years across. Our home galaxy, the Milky Way, contains hundreds of billions of stars. Every one of them is moving. Some race around the galactic center at more than 200 kilometers every second. Clouds of gas drift through space. Massive star clusters orbit like swarms of bees. Invisible objects lurk in the darkness. Even our own sun is hurtling through the galaxy at extraordinary speed. Yet despite all this motion, the Milky Way has remained together for billions of years. It doesn't unravel. It doesn't scatter into intergalactic space. It doesn't slowly dissolve until every star wanders away. Considering the incredible speeds involved, that seems almost impossible. So what is holding an entire galaxy together? And even more strangely, why do astronomers believe that most of what holds the Milky Way together cannot actually be seen? To answer that question, we have to begin by forgetting something our everyday experience has taught us. On Earth, large collections of objects don't naturally stay together unless something physically connects them. Buildings rely on steel beams, bridges need cables. Solar systems seem understandable because planets orbit a single bright star. But a galaxy isn't built that way. There is no gigantic framework supporting hundreds of billions of stars. There are no cosmic walls, no invisible ropes stretching across space. Stars are separated by enormous distances. If our sun were the size of a grain of sand, the nearest star would be several hundred kilometers away on the same scale. Even inside a galaxy, space is overwhelmingly empty. Yet somehow this enormous collection behaves almost like a single living structure. Understanding why requires us to rethink gravity on a scale far beyond anything humans naturally imagine. For thousands of years, gravity seemed simple. Things fall downward. Throw a stone and eventually it lands. Drop an apple and Earth pulls it back. Then in the 17th century, Isaac Newton proposed something revolutionary. Gravity was not unique to Earth. Every object in the universe attracts every other object. Even two tiny pebbles exert a gravitational pull on one another. The force is incredibly weak for small objects, but when enough mass gathers together, gravity becomes the architect of the universe. Newton described this with one elegant relationship. The gravitational force between two objects increases with their masses and decreases with the square of the distance separating them. This simple law explains why the Moon orbits Earth, why Earth orbits the Sun, and why planets remain bound inside the solar system. For centuries, it seemed almost magical that one mathematical equation could describe both a falling apple and the motion of planets. But galaxies would eventually test whether our understanding of gravity was complete. Our solar system feels enormous to us. Neptune orbits nearly 5 billion kilometers from the Sun. Light itself needs over 4 hours to travel that distance. Yet compared to the Milky Way, the solar system is almost microscopic. The Sun takes about 230 million years to complete just one orbit around the galactic center. That means since dinosaurs first appeared on Earth, our solar system has completed only about one full journey around the galaxy, one orbit in all that time. This already hints at the immense scale involved. The center of the Milky Way lies roughly 26,000 light-years away from us. Even traveling at the speed of light, reaching it would take 26,000 years. Human civilization has existed for only a tiny fraction of that time. Distances this enormous create a fascinating problem. Gravity weakens with distance. So how can stars tens of thousands of light-years apart remain part of one stable system? At first glance, the answer seems straightforward. The combined gravity of all the stars should hold everything together. After all, hundreds of billions of stars represent an unimaginable amount of mass. Surely that would be enough. Astronomers once believed exactly that, but nature prepared an extraordinary surprise. Long before anyone understood galaxies, scientists assumed they behaved somewhat like our solar system. In the solar system, planets farther from the sun move slowly. Neptune orbits nearly 5 billion kilometers from the sun. Light itself needs over 4 hours to travel that distance. Yet compared to the Milky Way, the solar system is almost microscopic. The sun takes about 230 million years to complete just one orbit around the galactic center. That means since dinosaurs first appeared on Earth, our solar system has completed only about one full journey around the galaxy, one orbit in all that time. This already hints at the immense scale involved. The center of the Milky Way lies roughly 26,000 light-years away from us. Even traveling at the speed of light, reaching it would take 26,000 years. Human civilization has existed for only a tiny fraction of that time. Distances this enormous create a fascinating problem. Gravity weakens with distance, so how can stars tens of thousands of light-years apart remain part of one stable system? At first glance, the answer seems straightforward. The combined gravity of all the stars should hold everything together. After all, hundreds of billions of stars represent an unimaginable amount of mass. Surely that would be enough. Astronomers once believed exactly that, but nature prepared an extraordinary surprise. Long before anyone understood galaxies, scientists assumed they behaved somewhat like our solar system. In the solar system, planets farther from the sun move slowly. Neptune orbits nearly 5 billion kilometers from the sun. Light itself needs over 4 hours to travel that distance. Yet compared to the Milky Way, the solar system is almost microscopic. The sun takes about 230 million years to complete just one orbit around the galactic center. That means since dinosaurs first appeared on Earth, our solar system has completed only about one full journey around the galaxy, one orbit in all that time. This already hints at the immense scale involved. The center of the Milky Way lies roughly 26,000 light-years away from us. Even traveling at the speed of light, reaching it would take 26,000 years. Human civilization has existed for only a tiny fraction of that time. Distances this enormous create a fascinating problem. Gravity weakens with distance, so how can stars tens of thousands of light-years apart remain part of one stable system? At first glance, the answer seems straightforward. The combined gravity of all the stars should hold everything together. After all, hundreds of billions of stars represent an unimaginable amount of mass. Surely that would be enough. Astronomers once believed exactly that, but nature prepared an extraordinary surprise. Long before anyone understood galaxies, scientists assumed they behaved somewhat like our solar system. In the solar system, planets farther from the sun move more slowly. Mercury races around the sun in just 88 days. Earth takes 1 year. Neptune requires 165 Earth years. This pattern makes perfect sense. Closer planets experience stronger gravity, so they must move faster to remain in orbit. Farther planets feel weaker gravity and therefore orbit more slowly. If galaxies followed the same logic, stars near the center should orbit rapidly, while stars near the outer edge should move much slower. It seemed inevitable. Physics predicted it. Mathematics agreed. No one expected otherwise. Then astronomers began measuring the actual speeds of stars, and the universe quietly disagreed. Instead of slowing down, stars near the outer regions of galaxies continued moving astonishingly fast, sometimes almost as fast as stars much closer to the center. This wasn't a tiny discrepancy, it was enormous. According to Newtonian gravity, many of those stars should have escaped long ago. Imagine spinning a ball attached to a string. Spin slowly and the string keeps the ball moving in a circle. Spin too fast, and if the string breaks, the ball flies away instantly. Astronomers realized that galaxies appeared to have the opposite problem. The stars were spinning so rapidly that the visible matter simply wasn't providing enough gravitational string to hold them in. By every calculation based only on the stars, gas, and dust that telescopes could see, the Milky Way should gradually fly apart. But it doesn't. And every night we look into the sky, that impossible stability silently reminds us that something fundamental is still missing from our picture of the universe. The puzzle became even stranger when astronomers realized that the Milky Way was not unique. Everywhere they looked, galaxies displayed the same impossible behavior. Tiny galaxies, giant spiral galaxies, elliptical galaxies, even galaxies billions of light years away, whose light began traveling toward Earth long before multicellular life existed. Again and again, the numbers refused to match the predictions. If this were merely a problem with one galaxy, astronomers might suspect an unusual event, a collision, a hidden cluster of stars, or an error in measurement. But when nearly every galaxy behaves the same way, coincidence becomes an unlikely explanation. Instead, it suggests that the universe itself is trying to reveal something. The challenge, however, was proving it. Measuring the speed of a star inside another galaxy is far from easy. These stars are so distant that many appear as tiny points of light, even through powerful telescopes. Astronomers cannot simply watch one complete orbit. Some stars require hundreds of millions of years to circle their galaxy. Instead, they relied on one of physics's most powerful tools, light. When an object moves towards us, its light shifts slightly towards shorter wavelengths, becoming a little bluer. When it moves away, the light stretches toward longer wavelengths, becoming redder. This phenomenon is called the Doppler effect. Most people have heard it without realizing it. As an ambulance approaches, its siren sounds higher. As it passes and moves away, the pitch suddenly drops. The sound waves themselves are being compressed and stretched by motion. Light behaves remarkably similarly. Using sensitive spectrographs, astronomers can measure these tiny shifts with extraordinary precision. Even a minute change in wavelength reveals how fast a star is moving along our line of sight. By observing countless stars across a galaxy, scientists can reconstruct how the entire galaxy rotates. This technique transformed galaxies into beautiful pictures, into measurable physical systems, and the measurements became impossible to ignore. The outer stars simply refused to slow down. One scientist would become especially important in uncovering this mystery. In the late 20th century, astronomer Vera Rubin devoted years to studying how spiral galaxies rotate. Working alongside instrument maker Kent Ford, who had developed highly sensitive spectrographs, Rubin measured stellar motions with unprecedented accuracy. At the time, many researchers still believed the discrepancies would disappear as better observations became available. Instead, Rubin's data strengthened the mystery. Galaxy after galaxy showed nearly flat rotation curves. This phrase may sound technical, but it describes one of the most astonishing discoveries in modern astronomy. Imagine drawing a graph. The horizontal axis represents your distance from the center of a galaxy. The vertical axis represents the speed of stars. If visible matter were all that existed, the graph should rise near the center and then steadily decline outward, much like the orbital speeds of planets around the Sun. Instead, the graph rises and then remains almost flat. Stars tens of thousands of light years farther from the center continue moving at nearly the same speed. It is as though gravity refuses to weaken as expected. Rubin herself approached these results cautiously. Extraordinary claims require extraordinary evidence, and she spent years checking instruments, repeating observations, and comparing galaxies. The pattern persisted. Eventually, the astronomical community could no longer dismiss it. Her work became one of the strongest pieces of evidence that our picture of the universe was incomplete. Today, Vera Rubin is recognized as one of the most influential astronomers in history, not because she solved the mystery, but because she demonstrated beyond reasonable doubt that the mystery was real. At first, scientists searched for ordinary explanations. Perhaps telescopes were simply missing enormous numbers of faint stars. Maybe there were vast clouds of cold gas too dim to detect. Could countless dead stars, black dwarfs, brown dwarfs, or rogue planets account for the missing gravity? Each possibility was investigated carefully. Astronomy is built on skepticism. Before proposing something entirely new, researchers exhaust every conventional explanation. Radio telescopes mapped neutral hydrogen gas across galaxies. Infrared observatories searched for cool objects hidden by dust. X-ray telescopes examined energetic regions invisible to optical instruments. Space telescopes and ground-based observatories combined observations across the electromagnetic spectrum. Yet no matter how the calculations were refined, the conclusion remained. Visible matter accounted for only a small fraction of the gravity required. Imagine balancing a scale. On one side sits everything we can directly observe: stars, planets, gas clouds, nebulae, black holes, star clusters, and dust. On the other side sits the gravity actually measured. The gravitational side outweighs the visible side by roughly a factor of 5. Something contributes enormous mass without producing detectable light. That realization forced astronomers to consider an idea that initially sounded almost absurd. Perhaps most of the Milky Way is invisible. When people hear the phrase dark matter, many imagine some kind of black fog filling space. The name is unfortunately misleading. Dark matter is not simply ordinary matter that happens to be dark. A lump of coal is dark. A cold planet is dark. An isolated black hole emits no visible light. Yet all of these interact with electromagnetic radiation in predictable ways. Dark matter appears fundamentally different. It neither emits light, nor reflects it, nor absorbs it in any measurable way. If a beam of visible light passes through a region filled with dark matter, the light travels almost as though nothing were there. This is extraordinary. Nearly everything familiar in the universe interacts with light. Atoms absorb photons. Electrons emit photons. Molecules scatter photons. Even objects we call black are still interacting with light by absorbing most of it. Dark matter appears almost completely indifferent. Its presence is revealed mainly through gravity. This is why astronomers often say they do not see dark matter directly. Instead, they observe what gravity is doing. Imagine walking through fresh snow after someone invisible has crossed a field. You never see the person, but the footprints reveal that someone passed through. Dark matter is similar. The universe is filled with gravitational footprints. Galaxies rotate too quickly. Galaxy clusters remain bound. Light bends more strongly than visible matter alone can explain. Again and again, gravity points towards something unseen. The Milky Way itself provides one of the clearest examples. Our galaxy is not just a flat spiral disk of stars. Surrounding it is an enormous invisible structure extending far beyond the luminous spiral arms. Astronomers call this a dark matter halo. The word halo can be misleading because it suggests a thin ring. In reality, it is believed to be a vast three-dimensional distribution enveloping the entire galaxy. If you could somehow make the dark matter visible, the Milky Way would no longer resemble a bright pinwheel floating in empty space. Instead, the familiar spiral would occupy only the inner region of an enormous, nearly spherical cloud extending hundreds of thousands of light years into space. In fact, the visible galaxy may represent only a small luminous island embedded within this immense gravitational structure. This halo contains far more mass than all the stars combined. The stars, planets, nebulae, and even the supermassive black hole at the galactic center contribute only a fraction of the Milky Way's total mass. Most of the galaxy's gravitational influence comes from something we cannot yet identify. That realization changes how we picture our place in the cosmos. When you look up at the Milky Way on a dark night, you are seeing only its brightest skeleton. The true galaxy, at least in terms of mass, is almost entirely invisible. And that raises an even deeper question. If the invisible part dominates the galaxy, then is the visible universe merely a small fraction of what truly exists? The answer begins far beyond the Milky Way itself, in the largest structures ever discovered, where gravity reveals patterns on scales so immense that they reshape our understanding of the entire universe. The Milky Way is only one member of a much larger cosmic family. It belongs to a collection known as the Local Group, a gravitationally bound neighborhood containing more than 100 galaxies. Some are tiny dwarf galaxies with only a few million stars. Others, like the Andromeda Galaxy, rival or even exceed the Milky Way in size. Despite the unimaginable distances between them, these galaxies are not drifting aimlessly through space. They influence one another. The Milky Way and Andromeda, separated by about 2.5 million light-years, are slowly falling toward each other under the pull of gravity. In roughly 4 to 5 billion years, they're expected to collide and eventually merge into a single, larger galaxy. That collision sounds catastrophic. Movies often portray galaxies smashing together like cars in a highway crash. Reality is far stranger. Because stars inside galaxies are so widely separated, direct stellar collisions are extraordinarily unlikely. If the Sun were as big as a marble, the nearest star would still be thousands of kilometers away on the same scale. Instead of stars crashing into one another, gravity slowly reshapes the entire structure. The galaxies pass through each other. Their gas clouds collide. New waves of star formation ignite. Their spiral arms become distorted. Over hundreds of millions of years, the graceful spirals disappear, replaced by one enormous elliptical galaxy. Once again, gravity, not physical contact, is doing almost all the work. This demonstrates something remarkable. Gravity does not merely hold together individual stars or planets. It organizes structures across millions of light-years. But this also creates another puzzle. If gravity is responsible for binding galaxies, what is responsible for building galaxies in the first place? How did the Milky Way ever become a galaxy instead of remaining a scattered cloud of stars? To answer that, astronomers had to travel backward, not through space, but through time. Every telescope is a time machine. Light does not arrive instantly. It travels at approximately 300,000 kilometers every second. When you look at the moon, you see it as it was about 1.3 seconds ago. The sun appears as it was roughly 8 minutes ago. The Andromeda Galaxy appears as it existed about 2.5 million years ago. And the most distant galaxies ever observed are seen as they were over 13 billion years in the past. Looking deeper into space literally means looking earlier in cosmic history. This allows astronomers to watch galaxies at different stages of evolution. Nearby galaxies appear mature. Distant galaxies often look smaller, messier, and far less organized. Some resemble irregular clumps rather than elegant spirals. Others seem to be merging. Some are experiencing furious bursts of star formation, unlike anything common today. It is almost like flipping through an ancient family photo album of the universe. The farther back we look, the younger galaxies become. This remarkable fact has allowed astronomers to reconstruct one of the greatest stories ever discovered. Galaxies were not created fully formed. They grew. According to our current understanding, the universe began approximately 13.8 billion years ago in an extremely hot, dense state. During its earliest moments, matter was distributed with astonishing uniformity. Not perfectly uniform, but very close. Tiny fluctuations existed. Some regions contained just a little more matter than others. These differences were incredibly small. The temperature variations preserved in the cosmic microwave background are only about 1 part in 100,000. To human eyes, such differences would appear insignificant. To gravity, they were everything. Gravity has a remarkable characteristic. It amplifies small differences. Imagine rainwater flowing across a perfectly flat field. The slightest depression collects a little more water. That extra water deepens the depression, which attracts even more water. Over time, tiny differences grow into streams and rivers. Gravity behaves similarly. Regions containing slightly more matter exerted slightly stronger gravitational attraction. That stronger gravity pulled in additional matter, which increased their gravity even further. Over hundreds of millions of years, tiny fluctuations became enormous cosmic structures. This process is known as gravitational instability, and it is one of the central ideas in modern cosmology. Without it, galaxies would never have formed. Yet, something about this picture still doesn't add up. If only ordinary matter existed, nearby galaxies appear mature. Distant galaxies often look smaller, messier, and far less organized. Some resemble irregular clumps rather than elegant spirals. Others seem to be merging. Some are experiencing furious bursts of star formation unlike anything common today. It is almost like flipping through an ancient family photo album of the universe. The farther back we look, the younger galaxies become. This remarkable fact has allowed astronomers to reconstruct one of the greatest stories ever discovered. Galaxies were not created fully formed, they grew. According to our current understanding, the universe began approximately 13.8 billion years ago in an extremely hot, dense state. During its earliest moments, matter was distributed with astonishing uniformity. Not perfectly uniform, but very close. Tiny fluctuations existed. Some regions contained just a little more matter than others. These differences were incredibly small. The temperature variations preserved in the cosmic microwave background are only about 1 part in 100,000. To human eyes, such differences would appear insignificant. To gravity, they were everything. Gravity has a remarkable characteristic. It amplifies small differences. Imagine rainwater flowing across a perfectly flat field. The slightest depression collects a little more water. That extra water deepens the depression, which attracts even more water. Over time, tiny differences grow into streams and rivers. Gravity behaves similarly. Regions containing slightly more matter exerted slightly stronger gravitational attraction. That stronger gravity pulled in additional matter, which increased their gravity even further. Over hundreds of millions of years, tiny fluctuations became enormous cosmic structures. This process is known as gravitational instability, and it is one of the central ideas in modern cosmology. Without it, galaxies would never have formed. Yet something about this picture still doesn't add up. If only ordinary matter existed, the process would have been painfully slow. The expanding universe was carrying matter apart while gravity struggled to pull it together. Computer simulations showed that galaxies should not have formed as early as astronomers actually observed them. The universe seemed to have built galaxies too quickly, unless something invisible began the process much earlier. This is where dark matter changes from a galactic mystery into a cosmic necessity. Unlike ordinary matter, dark matter appears not to interact significantly with light or radiation. In the early universe, ordinary matter was constantly colliding with energetic photons. It behaved almost like a glowing cosmic fog. Those interactions prevented ordinary matter from collapsing efficiently under gravity. Dark matter, however, was different. Because it interacted very weakly with radiation, it could begin clumping much earlier. Long before the first stars ignited, long before galaxies acquired their spiral arms, immense dark matter structures were already forming. These invisible concentrations acted like gravitational scaffolding. Ordinary gas gradually fell into them. As the gas became denser, it cooled. Eventually, gravity compressed portions of that gas until nuclear fusion ignited. The first stars were born. Those stars gathered into the first galaxies. Over billions of years, mergers and continued accretion transformed those primitive systems into the magnificent galaxies we observe today. If this picture is correct, then something extraordinary follows. The Milky Way did not form first and later acquire dark matter. Quite the opposite. Its invisible foundation may have existed before the galaxy itself. The stars that paint our night sky could simply be the visible decoration on an ancient gravitational framework established near the dawn of cosmic history. How can scientists test such an astonishing idea? One powerful approach is something called computer cosmology. Modern supercomputers solve the equations governing gravity for billions of particles simultaneously. Researchers begin with conditions measured from the cosmic microwave background, the oldest light in the universe. They then allow gravity to evolve the simulated universe over billions of years. When simulations include only ordinary matter, the resulting universe looks wrong. Galaxies emerge too late. Large-scale structures fail to resemble reality. The distribution of galaxies disagrees with observations. But when researchers include a dominant component behaving like dark matter, something remarkable happens. Filaments appear, clusters grow, galaxies form at approximately the correct times. The large-scale structure begins to resemble the actual universe. These simulations produce a breathtaking image known as the cosmic web. Instead of galaxies being scattered randomly through space, they arrange themselves into an immense network of interconnected filaments stretching across hundreds of millions of light years. At the intersections of these filaments lie giant galaxy clusters. Between them are enormous voids, regions containing comparatively little matter. The Milky Way itself occupies only a tiny position within this incomprehensibly vast architecture. It is as though the universe possesses an invisible skeleton. Galaxies are not isolated islands. They are nodes within a gigantic gravitational network extending across the observable cosmos. And according to current models, much of that skeleton is built from dark matter. The existence of this cosmic web raises an unsettling possibility. What if gravity alone is not merely holding galaxies together? What if gravity has been quietly shaping almost every large structure in the universe since the first moments after the Big Bang? If that's true, then understanding why the Milky Way doesn't fly apart requires understanding gravity at a level far deeper than Newton ever imagined. Because by the early 20th century, astronomers had begun realizing that Newton's magnificent theory, while astonishingly accurate for planets and moons, might not tell the whole story when space, time, and entire galaxies are involved. And that realization began with one of the most profound ideas ever proposed by Albert Einstein. For more than 2 centuries, Newton's law of gravity explained the universe with astonishing success. It predicted the motion of planets, it explained the tides, it described the paths of comets. Engineers still use Newton's equations to launch satellites and send spacecraft to distant planets. If humanity can land a rover on Mars using Newtonian mechanics, why should we question it at all? Because every great scientific theory has limits. Newton imagined gravity as an invisible force acting instantly across empty space. If the sun could somehow disappear, Newton's equations implied that Earth would immediately stop orbiting and fly off into space. But there was a problem. Nothing in nature appears to travel infinitely fast. Light has a finite speed. Sound has a finite speed. Even gravity, Einstein suspected, should not act instantaneously. That seemingly small idea forced physicists to rethink one of the deepest assumptions in science. Instead of asking, what force pulls objects together, Einstein asked a completely different question. What if nothing is pulling them at all? In 1915, Albert Einstein introduced the general theory of relativity. It remains one of the most beautiful and astonishingly successful theories ever created. Rather than describing gravity as a force, Einstein described it as the geometry of space-time itself. This sounds abstract, but imagine standing on a perfectly flat rubber sheet. Now place a heavy bowling ball in the center. The sheet bends. Roll a marble nearby. The marble curves toward the bowling ball, not because an invisible hand is pulling it, but because the surface beneath it has changed shape. Of course, the real universe is not a two-dimensional sheet. It has 3 dimensions of space and 1 dimension of time woven together into a 4-dimensional fabric called space-time. Mass and energy tells space-time how to curve. Curved space-time tells matter how to move. That single sentence summarizes an idea so profound that it changed physics forever. The Earth is not being pulled toward the sun in the ordinary sense. Instead, Earth follows the straightest possible path through curved space-time. Its orbit is simply the natural consequence of moving through a geometry distorted by the sun's mass. Even light, which has no mass, must follow this curved geometry. That prediction sounded unbelievable. How could gravity affect something that has no mass? Yet Einstein insisted it must, and just 4 years later, nature proved him right. In 1919, British astronomer Arthur Eddington organized an expedition to observe a total solar eclipse. Normally, the sun's brilliant light hides the stars behind it, but during an eclipse, the moon blocks the sun, allowing those background stars to become visible. Einstein predicted something extraordinary. Their apparent positions should shift slightly, because their light would bend while passing through the curved space-time around the sun. The effect was tiny, less than 2 arcseconds, equivalent to viewing a coin from several kilometers away. Yet Eddington measured exactly the kind of shift Einstein had predicted. Newspapers around the world declared that a new theory of the universe had arrived. Whether every detail of that historic observation would satisfy today's standards remains debated by historians of science. But over the following century, the prediction has been confirmed repeatedly with far greater precision. Today, gravitational lensing is one of astronomy's most powerful tools, and ironically, it would become one of the strongest pieces of evidence that the Milky Way contains far more mass than we can see. Imagine looking at a distant galaxy through a gigantic magnifying glass. The image stretches, it bends, sometimes it splits into multiple copies, sometimes it forms complete rings around a foreground object. These spectacular phenomena are called gravitational lenses, but there is no glass, no mirror, no optical device of any kind. The lens is gravity itself. When light from a distant galaxy travels through curved space-time surrounding another massive object, its path changes. The more mass present, the greater the bending. This allows astronomers to do something extraordinary. They can weigh objects using light, not by measuring what shines, but by measuring how much space-time is curved. Suppose a galaxy cluster bends background light far more strongly than expected. Astronomers calculate the amount of visible matter inside the cluster. Stars contribute one amount, gas contributes another. Black holes add a little more. Yet after adding everything together, the predicted bending remains far too small. Something else must be curving space-time. Something massive, yet invisible. This conclusion has now been reached thousands of times across the universe. Different telescopes, different research groups, different methods. The answer keeps pointing in the same direction. Most of the mass is hidden. One of the most compelling examples came from an event that occurred hundreds of millions of light-years away. 2 enormous galaxy clusters collided. This system became known as the bullet cluster. At first glance, it appears to be an ordinary collision, but astronomers examined it using multiple telescopes, each revealing a different component of the event. Optical telescopes showed where the galaxies were. X-ray observatories revealed immense clouds of superheated gas. Since gas is ordinary matter, it behaves differently during collisions. The gas clouds slammed into one another, slowed dramatically, and remained near the center. The galaxies themselves mostly passed by each other because the distances between stars are so vast. Then, astronomers mapped the gravitational lensing. They expected the strongest gravity to coincide with the hot gas, since that contained most of the ordinary matter. Instead, the strongest gravitational field followed the galaxies, not the gas. It was as though most of the mass had ignored the collision entirely. The observation was astonishing. If dark matter exists as a separate component of the universe, this is exactly what should happen. Ordinary matter collides. Dark matter barely interacts except through gravity, so it continues moving almost undisturbed. The bullet cluster did not prove dark matter beyond all possible doubt. Science rarely works that way. But it provided one of the clearest pieces of evidence that the missing mass behaves differently from ordinary matter. The invisible component appeared to separate from the visible one, almost like watching the shadow of an object continue moving after the object itself has slowed down. Still, not every physicist agrees that dark matter is the only explanation. Whenever a mystery survives for decades, scientists naturally begin asking a different question. Perhaps the missing matter isn't missing at all. Perhaps our theory of gravity becomes incomplete on galactic scales. This idea has led to several alternative theories, the most famous being modified Newtonian dynamics, or MOND, proposed by physicist Mordecai Milgram in the early 1980s. Instead of adding invisible matter to the universe, MOND suggests that gravity behaves slightly differently when accelerations become extremely small, precisely the regime found in the outer regions of galaxies. Remarkably, MOND can reproduce many observed galactic rotation curves with surprising accuracy. That success means it cannot simply be dismissed. It serves as an important reminder that science advances by testing competing ideas, not by becoming attached to a single explanation. However, MOND faces serious challenges. It struggles to explain galaxy clusters as naturally as dark matter models. It has difficulty accounting for the detailed structure of the cosmic microwave background, and reproducing the full cosmic web seen in large-scale surveys remains far more successful within the framework of dark matter and general relativity. For this reason, the majority of cosmologists currently favor the dark matter interpretation. But the debate itself is valuable. It reminds us that our understanding of gravity may still be incomplete. History has shown that whenever nature refuses to fit our equations, one of two things is usually true. Either we have overlooked something in the universe, or we have overlooked something in our theories. Sometimes, as happened with Einstein, both turn out to be true. And nowhere is that possibility more intriguing than at the very heart of the Milky Way, where an object so extreme that even light cannot escape may also play a role in holding our galaxy together, or perhaps far less of a role than most people imagine. There is one final realization that changes the way we see our place in the universe. When we ask, why doesn't the Milky Way fly apart, we naturally imagine that something must be physically holding the galaxy together, almost like glue holding pieces of wood. But nature doesn't work that way. The Milky Way survives because every star is constantly falling through curved space-time, each one following the invisible paths carved out by gravity. Our sun, carrying Earth and every living thing upon it, has been falling around the galactic center for more than 4 billion years. We are not passengers on a stationary world. We are travelers moving through an immense gravitational landscape that has existed for billions of years. Yet the greatest surprise is that the stars themselves are only a small part of that landscape. Everything we can see, the glowing spiral arms, brilliant nebulae, star clusters, planets, and even the supermassive black hole Sagittarius A at the galaxy's center, accounts for only a fraction of the Milky Way's total mass. The overwhelming majority appears to be something invisible, forming a vast dark matter halo that extends far beyond the visible galaxy. If current models are correct, the beautiful band of light stretching across our night sky is merely the illuminated core of a much larger cosmic structure that our eyes can never directly perceive. And that leaves us with one of the most profound mysteries in all of science. We have mapped galaxies across billions of light years. We have measured the expansion of the universe. We have detected gravitational waves from merging black holes and photographed the shadow of a supermassive black hole Sagittarius A at the galaxy's center. Yet we still do not know what makes up most of the matter holding galaxies together. The answer may come from underground particle detectors, future space telescopes, more powerful simulations, or perhaps from a completely new theory of physics that reshapes our understanding of gravity itself. So the Milky Way doesn't fly apart because gravity, most of it generated by matter we cannot see, binds it into a single cosmic system. But that explanation is only the beginning. Every orbiting star, every rotating galaxy, and every filament of the cosmic web points toward a deeper truth. The universe is still keeping some of its most important secrets. And perhaps the greatest discovery awaiting humanity is not a new planet or a new galaxy, but an entirely new understanding of what the universe is truly made of. Until then, each time you look up at the faint river of stars crossing the night sky, remember that you are seeing only a small fraction of your home galaxy. Most of the Milky Way is invisible, its gravity silently guiding the motion of hundreds of billions of stars, including our own Sun, as it continues a journey that has lasted for nearly 13 billion years. The galaxy remains intact, not because the mystery has been solved, but because the universe still has more to teach us.